Hi and welcome to this Leaving Cert higher level revision video. Today we're going to be reviewing proof by induction.
So proof by induction has a few different elements. So the first element is the proposition. So this is the thing that you want to prove, and we generally use the notation Pn for that. We then start with a base case. So that is usually subbing in 1 instead of n. Now this will change slightly depending on the question and what we're trying to prove, but in the majority of cases we're just going to be doing n equals 1. We then have an inductive step, which basically we're going to take pk, which is basically let n equals k. We're going to assume that to be true, and then we're going to use that to help us to prove that when n is equal to k plus 1, it's also true. We then end with the conclusion. So it's a very rigorous step-by-step process. There are a few different types of proof by induction questions we can meet, and we'll cover them over the next few days. But to break it down, I'm going to give you an easier step-by-step layout that we will use in every single question. So this layout will differ depending on where you see it. Everyone has like their own version of this, but the elements should all be the same. So first thing we're going to do is we're going to write our proposition, Pn. We then show that it's true for n equals 1. That's step 1. So that's effectively P1. We then, for step 2, assume it's true for n equals k. So all that involves is basically subbing in k instead of n, and we stop. There's no proving. We just write that statement and we can say that that is true. We're assuming that. Step 3 is then prove true for n equals k plus 1. So that's p of k plus 1. And when we've proven that to be true, we end all of our questions with a conclusion. So the conclusion that I like to use is the proposition is true for n equals 1. And if the proposition is true for n equals k, then it will be true for n equals k plus 1. Therefore, by induction, it is true for all n element of the natural numbers. Now, parts that will change depending on the question. So we mightn't start at 1. It mightn't be true for all n element of the natural numbers. It might be bigger than a certain number, but this is the bones of how we will approach every single question. So there's going to be 4 types of proof by induction questions we're going to see on the paper. So the first 3 are like groupings of proofs. We won't know for sure what exactly they are going to ask us to prove, but the steps will be pretty much the same. Doesn't matter what the question is. So they are series proofs, divisibility proofs, and inequality proofs. We then have the formal proof of de Moivre's theorem, which is a proof by induction. What's nice about the proof by induction for de Moivre is that actually there isn't as much learning off as we might see in the paper 2 theorems or the trigonometry proofs. So the first one we're going to look at is our series proofs. So our first example, prove that for all values of n, that 1 plus 2 plus 3 plus 4 plus ... all the way up to n is equal to n divided by 2, n plus 1. So let's follow our steps that you've hopefully taken down already. So we start off with our proposition, so Pn. So the proposition is that 1 plus 2 plus 3 plus 4 all the way up to n, and that should equal n over 2 times n plus 1. So then we start with step 1. So step 1, we're going to show, and we use the word show because it's not really a prove here. So show true for n equals 1. So we're literally going to take what we have above and sub in n equals 1. So this is P1. And we have 1 is equal to 1 over 2, 1 plus 1, 1 equals 1. So that is true. Then step 2. Step 2 is assume true for n equals k. So we're doing pk here. So we basically have 1 plus 2 plus 3 plus 4 all the way up to k this time, and that should equal k over 2 times k plus 1. And we're assuming that to be true. So we're not going to go any further. So the first two steps of this, very straightforward. And there should be absolutely no problem if you're asked proof by induction to do step 1 and 2. We then can set up step 3. And our step 3 is going to be prove true for n equals k plus 1. So this is p of k plus 1. So what we get is 1 plus 2 plus 3 plus 4. This time we're all the way up to k plus 1. And that should be equal to k plus 1 over 2, k plus 1 plus 1. So the trick in all these induction questions, and especially the series ones, is using step 2 to prove step 3. So we know step 2 is true. So what we're going to do on this left hand side, we're actually going to break it down into plus 3 plus 4 plus dot 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 plus k plus 1. And with this, we've already shown from step 2, or we've assumed from step 2, that this is k bracket k plus 1 and k over 2 plus, then we have a k plus 1. So that allows us to work with what we already know and should make it is so much easier now to prove. I'm just going to clean this up a bit. K plus 2. So we get k plus 1 times k plus 2 all over 2. And now we're going to rework that left hand side a little bit more just to try and make it look like that right hand side. You can do it whatever way you want. There's no issue. I would prefer to work with the left hand side and make it look like the right hand side, but if you were to make it balance in any way, it would be correct. So I'm going to do a lowest common denominator of 2. So we get k squared plus k, that's from what was previous there, plus 2k plus 2. So what I've done is I've actually put this over 2, and I've had to multiply the top by 2, and then I just combined it. I'm also going to multiply out this top line just to make it easier. Okay, k squared plus k plus 2k plus 2 all over 2, and we should end up with the same thing. So yeah, k squared plus 3k plus 2 all over 2. So we have proved that to be true. Just a bit of space, so we'll say therefore p k plus 1 is true. Now our last step is our conclusion. So our conclusion will refer back to the question, but the majority of it is just something we can learn off. So the proposition is true for n equals 1, and if the proposition is true for n equals k, so that's the one we assumed, then it will be true for n equals k plus 1. Therefore, by induction, it is true for, and this is where we refer back to the question, all values of n. So this part here is coming from the question. So we'll edit it slightly. We'll edit it slightly just to match what the question is asking, so we're not just saying the same thing every time. But that's it. So our proof by induction, there should be absolutely no problem doing step 1, step 2. You should be able to set up step 3. Step 3 is where sometimes there's a challenge to understand how we actually prove that to be true. So really that will be the focus. Once you get your steps, and today's class is all about focusing in on getting those steps and figuring out can I remember all my steps, step 1, step 2, step 3, the conclusion, writing your proposition, and so on. Tomorrow we'll look at Moivre with just that, and then we'll be looking even further into the divisibility and the inequalities. By the time you get to the inequality proofs, they're a bit more challenging, so really focus today on getting those steps. So the second example, prove that for all values of n element of natural numbers, this statement is true. So let's set this up. So this is the proposition. So the proposition is 3 plus 3 squared plus 3 cubed plus 3 to the power of 4 plus 3 to the power of 5 plus dot 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 all the way up to 3 to the power of n. That is equal to 3 over 2, 3 to the power of n minus 1. Okay, so now that I've done that, I move on to step 1. So step 1 is show true for n equals 1. So we're going to do P1, so proposition where n equals 1, and we get 3 is equal to 3 over 2 times 3 to the power of 1 minus 1, so that's 2, so therefore 3 is equal to 3, therefore true. You could also say something like therefore P1 is true if you want to use that notation. As long as you're showing it's true, it doesn't matter. So step 2, we're going to assume true for n equals k. And that is going to be pk. And we're going to have 3 plus 3 squared plus 3 cubed plus 3 to the power of 4 plus 3 to the power of 5 plus dot 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 plus 3 to the power of k. That's going to equal to 3 over 2 times 3 to the power of k minus 1. So we're assuming pk is true. So we haven't proved it, we're just assuming it. Okay, so then we're moving on to step 3. Prove true for n equals k plus 1. So first thing we're going to do is we're going to set it up. So that is proposition k plus 1. So where n is equal to k plus 1. And we're going to set this as 3 plus 3 power 2 plus, I'm just going to do dot 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 here, 3 to the power of k plus 1 is equal to 3 over 2, 3 to the power of k plus 1 minus 1. Now watch your indices there. K plus 1 is all part of the indice. Just like in the last example, we're going to use what we've already assumed to be true in part or step 2. So we're going to do dot 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 up to, we'd have 3 to the power of k, then 3 to the power of k plus 1. So all I'm doing is I'm writing in the second last term, because now I can use the fact that I've assumed that this is 3 over 2, 3 to the power of k minus 1, and that should be equal to k, 3 to the power of k plus 1. I'm going to just clean this up a little bit. 3 to the power of k plus 1 minus 1 all over 2. And I want to show that that is true. So I'm not going to do anything with this for 1 second. Minus 1 all over 2. The left hand side, I'm going to do a little bit of work. Again, I'm going to put it all over 2. So if I put that over 2, I'm going to multiply by 2. Now remember BIMDAS, so although I can write that multiplication, I can't actually do it. So what I get is 3 times 3 to the power of k minus 1 plus 2 times 3 to the power of k plus 1, and that's all over 2. And I want to show that that's 3 times 3 to the power of k plus 1 minus 1 all over 2. So the bottom line is absolutely fine for us. We're now just focusing in on that top line to make those top lines look the same. So I'm just going to clear the screen so we can work, we have space to work this through. I'm actually going to focus on that 3 to the power of k plus 1. So here I have 3 times 3 to the power of k minus 1, and this is 2, and I'm going to break this into 3 to the power of k times 3. So remember, we can work backwards in our laws of indices. So now, and if you prefer, if you don't want to keep writing this, you could take the left hand side and just work with the left hand side, just call it LHS and work there. But I'm going to pull it down through. I'm going to do highest common factor here. And the highest common factor, what's common in both is the 3, and that matches over here on the right hand side, so I'm on the right track. So I pull the 3 out, and that gives me 3 to the power of k minus 1 plus 2 times 3 to the power of k all over 2, and that is 3 times 3 to the power of k plus 1 minus 1 for 2. And now we're going to work this. So I have here, just so we can keep track, 3 to the power of k and 2 3 to the power of k. So if I have a 3 to the power of k and I add 2 more 3 to the power of k, what I actually get here is 3 to the power of k's and then a minus 1. So I'm very close to looking like what I want on that right hand side. And actually that 3 times 3 to the power of k is actually 3 to the power of k plus 1. Because remember, this can have a power of 1. So that's 3 times 3 to the power of k plus 1 minus 1 all over 2 is the same as 3 times 3 to the power of k plus 1 minus 1 all over 2. So what we've just proved, therefore p to the power of k plus 1 is true. So that step 3 is where all that work is. So it's the step 3 that you need to focus on. So our conclusion for this question is pretty much the same as what we had in the last one. The proposition is true for n equals 1. And if the proposition is true for n equals k, then it will be true for n equals k plus 1. Therefore, by induction, it is true. It is true. Let's go back to the question. For all values n element of the natural numbers. So example 3, prove by induction that this statement is true. Now, just be aware that dot is our dot product. So it's 1 times 2, 2 times 3, 3 times 4. We've never really seen the dot product used in the actual exams, but we do see it sometimes in books. a common question is, well, how would you know? Well, if you look at what that fraction ends up as, and I'll rub this out in a sec, but that has an n times n plus 1. So logically, it's going to be multiplication and not decimals. Also, these numbers, the n's are elements of n's, which are positive whole numbers. So don't panic too much about it, but just be aware that that is dot product. So let's set this up. We have the proposition Pn, which is 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 and so on, dot dot dot, all the way up to n times n plus 1, and we want to prove that that equals n over n plus 1. So step 1, we're going to show true for n equals 1. So that's P1, and that is 1 over 1 times 2. Is that the same as 1 over 2? And that is a half equals a half. True. Like I said, we could say so P1 is true. You can do something like that. We then are going to do step 2. We're going to assume true for n equals k. Oh, that k didn't come out very well. So n equals k. So that's the proposition of k, pk. And we get 1 over 1 times 2 plus 1 over 2 times 3 and dot 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 all the way up to k bracket k plus 1, and that should equal k over k plus 1. So we're just assuming, pk is true. So then the next step, I'm going to try to fit a little bit here before I clear the page. So step 3, we're going to prove true for n equals k plus 1. So what that means for us, plus 1, is we're going to have 1 over 1 times 2 plus 1 over 2 times 3 plus dot 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 1 over it's k plus 1 times k plus 1 plus 1. And that should all equal k plus 1 all over k plus 1 plus 1. So we have a little bit of cleanup to do, but just like in the other previous 2 examples, we're going to take what we know from step 2 and apply it to step 3 to try prove that step 3 is true. So just like before, what we're going to do is we're going to break the left hand side up into what we had from step 2. So we have 1 over 1 times 2 plus 1 over 2 times 3 plus dot dot dot, and we put in the second last term, which is k bracket k plus 1 plus, then we have our last term, and I'm going to clean that up slightly, so that's going to be k plus 2, and that is all equal to, or at least we want to prove that it's equal to, k plus 2. Now this piece here we have assumed true from step 2, and we've assumed that it is k over k plus 1. We then have plus 1 over k plus 1, tidy this up a bit, k plus 1 times k plus 2, and that will equal, or again we want to prove that it equals k plus 2. So we want the lowest common denominator, so I'm going to multiply this fraction by k plus 2 on the bottom, but also k plus 2 on the top. And what we end up with is k bracket k plus 2 plus 1 all over k plus 1 times k plus 2. And we're trying to break it down to k plus 1 all over k plus 2. So notice that the bracket has or sorry, the bottom line on the left has an extra bracket. So let's multiply out the top. So k squared plus 2k plus 1 all over k plus 1, k plus 2. We're going to need to do a little bit of cancelling, so that will involve some factorisation. So I'll break this down. Breaking that, so you can do this to the side if you want to use guide number, but this should be straightforward enough. We should get k plus 1 times k plus 1. It's the perfect square, so you could write it as k plus 1 squared if you want. But we end up with a little bit of cancelling that can happen because we have a common factor on the top and on the bottom. So that brings us down to k plus 1 over k plus 2 is equal to k plus 1 over k plus 2. So we've proved it. So therefore p k plus 1 is true. So the final step now is our conclusion. So then if the proposition is true for n equals 1, the proposition is true for n equals 1, and if the proposition is true for n equals k, then it'll be true for n equals k plus 1. Therefore, by induction is true for all n element of the natural numbers. So example 4 is an exam style question, so we're going to see how it has appeared on previous papers and also mock papers. So prove by induction that the sum of the first n natural numbers, 1 plus 2 plus 3 plus all the way to n, is n bracket n plus 1 over 2. So we're going to write our proposition first. So this time we actually have to set it up. Now I know it's pretty much set up, but they haven't given us this kind of equation. We have to put in the equal sign. That's literally all we have to do. But that's us setting up the proposition. That's how we want to show. So then step 1 is show it's true for n equals 1. So that's going to give us P1. So P1 is 1, and we want to prove, does that equal 1 times 1 plus 1 over 2, 2 over 2, so that's 1 equals 1. Therefore, P1 is true. We then have step 2, assume true for n equals k. So that is 1 plus 2 plus 3 plus ... all the way up to k. And that's k bracket k plus 1 over 2. And we're assuming that to be true. So we assume pk is true. We then have step 3. So prove true for n equals k plus 1. So this is pk plus 1. So we have 1 plus 2 plus 3 plus ... all the way up to k plus 1. And that should be equal to, or at least we're going to try prove that it's k plus 1 plus 1 all over 2. So just like in every other example, we're going to break this down into what we had in step 2. So that's putting in the second last term and then plus k plus 1. And we're going to try again, show that that's k plus 1 times k plus 2, just clean up that bracket, all over 2. So this piece here we've done in step 2, and we've said that this is k bracket k plus 1 over 2, so we've assumed that to be true. We want to add k plus 1, and we want to get that as k plus 1 times k plus 2 all over 2. So first thing I'm going to do is do a common denominator. So I'll put the second term, multiply that by 2 and put it over 2, and then combine. So I get k times k plus 1 plus 2 times k plus 1 all over 2, and that is k plus 1 times k plus 2 over 2. Now I have a little shortcut here that I want to show you. And what I think a lot of students would do on the left hand side now, we multiply out the brackets, you're going to get a quadratic and then factorize. However, you should spot now that we actually have factorization halfway done because 2 of the brackets are the same. So both of those brackets are k plus 1, which means it is a highest common factor, so I can pull that out. And when I pull that out, I'm left with k plus 2. It's like the second last line to last line of grouping, or even quadratic if you do guide number method. So that has saved us about 3 lines just by spotting, and I'll highlight it here. So by spotting that k plus 1, that bracket is the same. So we are now going to be able to say, therefore, k plus 1 is true. And last step, we'll just put in our conclusion. So the conclusion is the proposition is true for n equals 1. So if the proposition is true for n equals k, then it will be true for n equals k plus 1, and therefore by induction true for all n elements of the natural numbers. Now that n element of n was not in the question, however they did say the sum of the first n natural numbers. So we are talking about natural numbers, so it's absolutely valid to leave it like that. So just to remind you that we have basically 3 different types of proof by induction and then this de Moivre's theorem. So when we looked at the series proof, that could be asked in any way. We don't have a specific individual proof. However, this one that we're looking at today, de Moivre's theorem, is. So de Moivre's theorem is here on page 20 of your log tables, and we specifically deal with this left-hand part of it. We don't care about that final equals. So we've used this in complex numbers, so now we're just going to prove that it's true. Okay, so let's look at example 5, and it's given us our statement here. So we're going to have Pn, that is our proposition that we want to prove. Step 1 is show true for n equals 1. So let's do when n equals 1. We will get cos of theta plus I sine theta to the power of 1 is equal to cos 1 times theta. It's all a bit messy. Let me tidy that up a little bit. Cos of 1 times theta plus I sine 1 times theta. We know anything to the power of 1 is just itself, so we have the cos of theta plus I sine theta is equal to, I don't need that bracket, cos of theta plus I sine theta. So that's true. Therefore, P1 is true. So step 2, assume true for n equals k. So we're going to write out our proposition with k, and that is that cos theta plus I sine theta to the power of k equals cos k theta plus I sine k theta. So we are assuming, sorry, that k doesn't look very k-ish. So we're assuming pk is true. And we're going to use that in our next step. So step 3 is we're going to prove true for n equals k plus 1. So we have cos theta plus I sine theta to the power of k plus 1. We want to show that that's equal to cos of k plus 1 theta plus I sine k plus 1 theta. Now, just like everything we've done so far, we're going to break up the left-hand side to use what we've already assumed true in step 2. So we're going to break this into, well, using our laws of indices, cos of theta plus I sine theta to the power of k, and then cos theta plus I sine theta to the power of 1. So that's using our laws of indices to break that up. Now we've already worked out that this part here, I'm going to just work, because there's a lot going on here, I'm just going to work the left hand side here for a minute. So we've already said that this is cos of k theta plus I sine k theta, and we have cos of theta plus I sine theta. So we're going to multiply out these two brackets. So it's not particularly nice, so really do take care. So I'm going to break up my brackets. Cos of theta plus I sine theta plus I sine k theta times cos of theta plus I sine theta, and that gives us cos k theta times cos theta plus I cos, I like to pull that I out in front. It doesn't have to be, but I just find if it's in the middle it gets lost. It is multiplication, so it doesn't matter. Plus I sine k theta cos of theta plus I squared sine k theta sine of theta. Now, I squared is actually minus 1. So we get cos k theta cos of theta. Because the I squared will go to minus 1, so this one here, I'm going to do this next, but I'm going to sub in minus 1 there. So it's sine of k theta sine of theta plus. Now the next two, I'm dealing with these two pieces here, and they're both imaginary parts. So I'm going to combine them. So that's my I. So this is all the imaginary parts. Cos k theta sine theta plus sine k theta cos theta. Now, here we're going to need a little bit of help, and where we're going to find that help is in our log tables. These are effectively trigonometric identities. So we're going to go to our log tables. We're looking at the top of page 14, and we're looking about what exactly we can do with the real part. So the real part is this piece here, and we're going to use something, and then the imaginary part, which is this bit here. So this was the last line we finished on. Just to remind you, we are only working with the left hand side at the moment, and we're trying to make it equal to the right hand side. Well, I haven't had space here to put it in. Even in a copier or in an exam question, I don't think you'd have the space. You really just want to work with that left hand side. Now, I said we're going to look at the real part and the imaginary part and see what we can do. Top of page 14, we have cos minus sine. So what we're actually looking at is this one here. So that actually becomes the cos of a plus b. So that's going to be k theta plus theta. So that's what that boils down to, plus I. So now we look at the second one. Now this one's a little bit trickier because I have a cos and then a sine and then a sine and then a cos. There's a plus between them, but really what we're looking at is this one here. They're just backwards. So you see the way here, I'll try another color. It has cos and then sine. Here's our cos and sine. Then there's a plus and sine and cos, and here's our sine and cos. So basically what this one boils down to is I sine of k theta plus theta, and we want to prove that that is equal to, and if you go back to what we wanted to show that that was equal to, it was the cos of k plus 1 times theta plus I sine k plus 1 theta. So we're actually nearly there because we've highest common factor in these brackets. So I have this. If I pull out my theta, I could write it in front, but it'll take an extra line to clean it up. So theta is common, so I pull it out and I'm left with k plus 1. And that gives me exactly what we've been looking for. K plus 1 times theta plus I sine k plus 1 theta. So that's the little trick in here. Remember, this will be asked as is. So therefore, p k plus 1 is true. Okay, and then we just have our conclusion. So the proposition is true for n equals 1, and if the proposition is true for n equals k, then it'll be true for n equals k plus 1. Therefore, by induction, it is true for all n element of z plus which are positive integers, which is what they said in the question. So this is the first time we've seen a little bit of a change in here, just because they haven't said natural numbers. So just to be aware of that with your conclusion. And today, like I said, we're looking at divisibility. So we've looked at series proofs. Yesterday I went through the proof of Moivre's theorem, which isn't like a type of proof, but it is in itself a proof, and it's asked as is. These divisibility proofs, we can only look at examples, and they could ask something that is similar but not exactly the same. So let's jump into an example. Prove that for all n element of natural numbers, 3 is a factor of 4 to the power of n minus 1. So our proposition is slightly different here. We want to prove that 3 is a factor of 4 to the power of n minus 1. And that means 3 divides in evenly with no remainder. So let's show that that's true for n equals 1. So 4 to the power of 1 minus 1 is equal to 3. So 3 is a factor of 3. So that's true. Therefore, P1 is true. Then step 2. Now there's a few different ways that people approach this step 2. And I'm going to do it in a way that I think is the easiest method to do the workings for step 3. So even though step 2 there might be an easier way to write it, I think that can make step 3 harder. So what we're going to say is we want to assume that 4 to the power of k minus 1 is divisible by 3. So I'm going to write that can be written as 3 to the power of, 3 multiplied by some number m, where m is an element of our natural numbers. So basically that 3 divides evenly in. That's a nicer way, I think, to write it. In order for us to use that, we're going to actually just bring that 1 over. So we're going to have 3m plus 1. And you'll see why we do that in a second. So we're going to assume pk is true. So step 3, and this is the one that tends to be the really difficult part for divisibility proofs, but I think our step 2 will help us. So we want to prove that 4 to the power of k plus 1 minus 1 is divisible by 3. So let's work through that. I'm going to break this up as 4 to the power of k times 4. So that's using my laws of indices minus 1. Now, I want to use what I've done in step 2, so I'm going to replace this 4 to the power of k with what we had in step 2. So that's 3m plus 1. And that's times 4 minus 1. I'm going to multiply everything out. So I have 12m plus 4 minus 1. And that's 12m plus 3. And that can be written as 3 bracket 4m plus 1. So that means it is divisible. So, sorry, now clean all this up. So we can say therefore 3 is a factor. Therefore pk plus 1 is true. So that little bit of substitution from step 2, I think that makes these questions a lot easier. You'll see that there are other methods in the book, and if you prefer other methods, work away, as long as you're really clearly explaining how we know that that is true. So final step is our conclusion. So nothing new with our conclusion. The proposition is true for n equals 1. If the proposition is true for n equals k, then it would be true for n equals k plus 1. Therefore, by induction, it is true for all n element of n. So prove by induction that 8 to the power of n minus 7m plus 6 is divisible by 7 for all n element of the natural numbers. So let's write our proposition. So that is 8 to the power of n minus 7n plus 6 is divisible by 7. And then show true for n equals 1. So we have 8 to the power of 1 minus 7 times 1 plus 6. So that's 8 minus 7 plus 6. And that equals 7. And 7 is divisible by 7. Therefore, P1 is true. Step 2. Assume true for n equals k. So we get 8 to the power of k minus 7 times k plus 6. and we're able to say that this should be divisible by 7, so it can be written as 7 times some number m, and we said that m is an element in this case. In this case I'm going to say z because it could be positive or negative whole number. So we've written it as that. So we can rearrange this for substitution. So 8 to the power of k. So I'm going to get 8k. So I always want to find something I can sub in for 8k. So 8 to the power of k. So 7m plus 7k minus 6. So we're assuming true. Assume pk is true. So this allows me to do substitution in the next step. So step 3 is prove true for n equals k plus 1. So I have 8 to the power of k plus 1 minus 7 times k plus 1 plus 6. So that's the same as 8 to the power of k times 8 minus 7k minus 7 plus 6. And we have a substitution we can do here from step 2. So in step 2 we have 7m plus 7k minus 6 all times 8 minus 7k minus 1. I've just cleaned up that minus 7 plus 6. Multiplication 56m plus 56k minus 48 minus 7k minus 1. That gives me 56m plus 49k minus 49. And now to prove that it's divisible by 7, we try to factor out a 7, which we can, and we're left with 8m plus 7k minus 7, and that is divisible by 7. Therefore pk plus 1 is true. Now there are, like I said, other ways that this can be approached, but I do think that substitution from step 3 is probably the simplest way to do the step 3. So if you can remember in step 2 to isolate the thing to the power, then you'll be fine. Last thing we want is our conclusion. So the proposition is true for n equals 1. If the proposition is true for n equals k, then it'll be true for n equals k plus 1. Therefore, by induction, it is true for all n element of n. So example 8, this is a different type of example with a different way to approach it because we don't have a power. If you were to multiply out those brackets, you'd end up with like an n to the power of 3, an n to the power of 2 and so on. But in the last few examples, the n was in the power. So that will change how we'll approach it. So this is a different style of question. So again, we want to just set up our proposition. So we want to show that n times n plus 1 times n plus 2 is divisible by 3. And this kind of question is more like what we saw in this series proofs. So step 1, we're going to show true for n equals 1. So we want to show 1 times 1 plus 1 times 1 plus 2, and that equals 6. And that is divisible by 3. Therefore, P1 is true. Step 2, assume true for n equals k. So we're going to have k times k plus 1 times k plus 2, and we're going to assume above is divisible by 3. So like I said, a different way to approach it this time. So now we're going to have step 3. So prove true for n equals k plus 1. So we get k plus 1 times k plus 1 plus 1 times k plus 1 plus 2. And when we multiply that out, we get when we clean that up, we get x plus 1 times x plus 2 times x plus 3. Remember, we always want to come back to what we had. So this bracket we had, this bracket we had, and this one we didn't. So what we can think of this as is two brackets here multiplied by the third bracket. And if we thought about that, we could say that we'd split the brackets. So it would be k times k plus 1 times k plus 2 plus 3 times k plus 1 times k plus 2. Now, this left-hand piece is definitely divisible. Well, we've assumed that it's divisible by 3 because we've assumed it in step 2. And this part is divisible by 3 because there's a 3 at the front. So divisible by 3. Therefore, it is fully divisible by 3. So if each of its parts are divisible by 3, then the whole thing is divisible by 3. Therefore, pk plus 1 is true. And all we need now is our conclusion. So the conclusion is the proposition is true for n equals 1, and if the proposition is true for n equals k, then it'll be true for n equals k plus 1, and therefore, by induction, true for all n elements of the natural numbers. So final example, example 9, is an exam-style divisibility proof. So we're back to something to a power where n is the power. So let's go through this. 8 to the power of n minus 1 is divisible by 7 for all n element of our natural numbers. So our proposition, we want to say that 8 to the power of n minus 1 is divisible by 7. So step 1 is to show true for n equals 1. So 8 to the power of 1 minus 1 is 7. And 7 is divisible by 7. And since it's divisible by 7, P1 is true. Okay, so step 2, assume true for n equals k. So I'm going back to my method of this equal to a number. So 8 to the power of k minus 1, I'm going to assume that it's divisible by 7. So I'm going to write it as 7m, where m is where m is an element of the natural numbers. So what I'm going to do is I'm going to isolate the 8 to the power of k, and I'm going to be able to use substitution in the next part. So I'm going to assume pk is true. So I'm assuming that those two lines above are true. So step 3, prove true for n equals k plus 1. So 8 to the power of k plus 1 minus 1, and that it can be split up into 8 to the power of k times 8 minus 1. 8 to the power of k can be written as 7m plus 1 times 8 minus 1. So that gives me 56m plus 8 minus 1. So that's 56m plus 7. I want to show that 7 is a factor, or it's divisible by 7. So that gives me 8m plus 1. This is then definitely divisible by 7. And therefore, p to the power of k plus 1 is true. Final step, put in our conclusion. So the proposition is true for n equals 1. If the proposition is true for n equals k, then it will be true for n equals k plus 1. And therefore, by induction, it is true for all n element of the natural numbers. We again are on our final piece. We did series first. I then looked specifically at the proof of De Moivre's theorem, and then we did divisibility proofs yesterday, and today we're going to do our final one, which is inequality proofs. I think inequality proofs are the hardest ones that we see. They're the least intuitive, in the sense that if you haven't ever really seen an example of it, you might really struggle on how to do it. That being said, once you found the trick, it should be absolutely fine. So let's jump into example 10. So we're following on from yesterday's example. So prove by induction that 2 to the power of n is greater than n squared. And this is important for n greater than 5, where n is a natural number. So this time, and it's the first time really we've seen a question where we're not starting with n equals 1. Because if we start with n equals 1, then we're not following what they've asked us to do. So we're going to start this question with n equals 5, because they've told us that n is greater than or equal to 5. The first thing we're going to do is we're going to write down our proposition, which is 2 to the power of n is greater than n squared. The next step is show that true for n equals 5. So not 1 in this case, because if you try 1 it won't work. So we get 1, sorry, me saying don't use 1 and I put 1 in. So it's 5 squared. So 2 to the power of 5, oh, that should be a greater than sign here as well. It's going to show that that is greater than 5 squared. So we get 32 is greater than 25. That is true. Therefore, P1 is true. So the next is we're going to assume it true for n equals k, but specifically where k is greater than or equal to 5. So we're going to have pk, which is 2 to the power of k is greater than k squared. So we're going to assume true. So we're going to assume that this is true for k greater than or equal to 5. So step 3 is to prove true for n equals k plus 1. So we get 2 to the power of k plus 1, and that's greater than k plus 1 squared. Now, up to here, everything is as per usual, nothing different. But how we're going to use step 2 is important. So I'm going to take this in a different color, and I'm going to say this is from step 2. So we know from step 2 that 2 to the power of k is greater than k squared. Now, I have what I want to prove is 2 to the power of k plus 1. So I'm going to multiply both sides by 2. Because 2 times 2 to the power of k, that will give me 2 to the power of k plus 1, which is what I have on the left-hand side of the 2 proof. So this matches this. So just to remind you, I know we've assumed it. So we have assumed this to be true. Okay, so we're saying this is true. So this last line here is true. And we want to use that to prove the previous blue line above. So I know that 2 to the power of k plus 1 is bigger than 2k squared. And I want to see is 2 to the power of k plus 1 greater than k plus 1 squared. So what I'm going to do is I'm actually going to compare this side to this side. So I'm going to use the fact that, well, look, if change back to the color, I'm trying to get blue. If 2k squared, this thing here, was bigger than this thing here, k plus 1 squared, then everything would be okay. Because if that was bigger, we would be able to say, well, then this would also be, and I'll put it in here, this will be smaller than 2 to the power of k plus 1. So by this logic, we'd have proved that this was greater than that. So that's what we're doing. We're focusing in on this piece here. So we've taken those 2 yellow pieces above. So I want to prove that 2k squared is bigger than k plus 1 squared. Because if I prove that, then we've proved what we want. So I have 2k squared is greater than k squared plus 2k plus 1. Rearranging that, I get k squared minus 2k minus 1. I want to prove that that is greater than 0. If you remember back to how we did this, it was completing the square. So I'm going to write this as k minus 2 squared. When I do that, and run out of colours, that's k squared minus, that's minus 1. Good thing we check. So k minus 1, so that's minus 2k plus 1. that plus 1 was extra, so I need to take it away. Oh, wrong pen. So I'm going to take away 1, and then I already had a minus 1 there, greater than 0. So I have k minus 1 squared minus 2 is greater than 0. Is that true? Well, for any k greater than 5, yeah, that will be true. Because once I put in k equal to 5, that's 5 minus 1, which is 4. So 4 squared minus 2 will be positive. Therefore, any number bigger than 5 will be absolutely fine. True for k greater than or equal to 5. So now what I've done is I've said that 2k squared is greater than k plus 1 squared. But I know that this 2k squared is smaller than 2k plus 1 because that's from step 2. So just ignoring that middle bit, that proves that 2 to the power of k plus 1 is greater than k plus 1 squared. So there's a lot in that step 3. It's very different how we work with it. So if you need to go back through it again, do, and I'm just going to finish off that step 3 now. So just to finish it off, we'll have therefore the proposition of k plus 1 is true. This means then we can have our conclusion, and the proposition is true for n equals 5. Just be aware of that. That's to link back to the question. So it's not 1. And if the proposition is true for n equals k, then it'll be true for n equals k plus 1. Therefore, by induction, it'll be true for all n greater than or equal to 5, where n is an element of the natural numbers. So let's try another example. So this is n factorial, and factorial means you multiply all the numbers back from n to 1. So for example, if it was 3 factorial, it would be 3 by 2 by 1. I'm going to show that's greater than 2 to the power of n. They've told us that n is greater than or equal to 4, where n is an element of the natural numbers. So our proposition is n factorial is greater than 2 to the power of n, but n is greater than or equal to 4. And we're going to show that that's true for n equals 4. So what that means for us is 4 factorial should be greater than 2 to the power of 4. So you have a factorial button in your calculator that you can use to work that out. And that works out as 24 is greater than 16. Therefore, p to the power, proposition 4 is true. Step 2. Assume true for n equals k, where k is greater than 4. So we're going to have k factorial greater than 2 to the power of k. And we're going to assume true for k greater than or equal to 4. Then we have prove true for n equals k plus 1. So we have k plus 1 factorial is greater than 2 to the power of k plus 1. So now that we've set up what we want to prove is true, we're going to go back to what we had in step 2. And I'm going to change my color. So this is from step 2. And we're going to follow the same logic as we had in the previous example. So we have k factorial is greater than 2 to the power of k. Now, I have on the left hand side here a k plus 1 factorial. And what k plus 1 factorial means, and I'll do it up here, k plus 1 factorial. What that actually means is k plus 1 times k minus 1 all the way back down to 1. So actually this part here is just k factorial. So what I'm going to do to make the two left hand sides equal is I'm going to multiply both sides by k plus 1. And now what I've made on the left hand side is k plus 1 factorial. So now my two left-hand sides match, and I have 2 to the power of k times k plus 1. Remember, this is what we know. We know that this is true, and we want to prove that this line here is true. So I know that k plus 1 factorial is bigger than this here. So what I'm going to do is I'm going to work with, just like in the last example, this piece and this piece. So I know that k plus 1 factorial is greater than 2 to the power of k times k plus 1. So if I say, or if I can prove that 2 to the power of k times k plus 1 is greater than 2 to the power of k plus 1, so then that straight away will tell us, and I'll do what I did the last time, because we know that this on this side is a k plus 1 factorial, so by cutting out that middle piece we'll have proven what we want. So we're going to take the two pieces above and I'm going to try in some way and prove that these are equal, or rather that one, well, the inequality is true rather. So I'm going to work on that left hand side, well sorry, the right hand side, because there's not much I can do here on the left hand side. So this I can break down into 2 times 2 to the power of k, and now there's a 2 to the power of k on both sides, so I get k plus 1 is greater than 2, so k is greater than 1. Well, we're saying where n is greater than or equal to 4, so that is true. So we can, I'll move a little bit here. So therefore, I have this line here is greater than 2k plus 1. And therefore, pk plus 1 is true. So that k is greater than 1. So that was basically saying that this thing here is valid when k is greater than 1. But remember, we know that n is always going to be greater than or equal to 4. So it is valid. So the last thing we need to do is our conclusion. So the conclusion is the proposition is true for n is equal to 4. If the proposition is true for n equals k, then it will be true for n equals k plus 4. Therefore, by induction, it is true for all n greater than or equal to 4, where n is an element of our natural numbers. So example 12, prove that 1 plus x to the power of n is greater than or equal to 1 plus nx for n greater than or equal to 1, where n is an element of the natural numbers and x is a real number. So first thing we're going to do, we're going to state our proposition. So that's 1 plus x to the power of n is greater than or equal to 1 plus nx. Then step 1, show true for n equals 1. So we're going to do substitution here. So 1 plus x to the power of 1, is that greater than or equal to 1 plus 1 times x, and that is 1 plus x is greater than or equal to 1 plus x. It is equal to, so that's good, therefore P1 is true. So then we have step 2. So assume true for n equals k. So we're going to assume that 1 plus x to the power of k is greater than or equal to 1 plus kx. So we assume pk is true. So step 3, prove true for n equals k plus 1. So let's set up that proposition. So we have 1 plus x to the power of k plus 1 is equal to 1 plus k plus 1, oh sorry, that should be a greater than or equal to, times x. Now that's what I want to prove. So what I do is I go to my step 2 and I take what we've already assumed to be true, which is 1 plus x to the power of k is greater than or equal to 1 plus kx. I want to make this left-hand side the same as this left-hand side. So in order to do that, I'm going to multiply it by a 1 plus x. So when I do that, that will end up giving me a 1 plus x to the power of k plus 1 using our laws of indices. Over here we get 1 plus x times 1 plus kx. So now I have the two, I'm not going to clean this up, I'm going to leave this as is. I have the two left-hand sides of the inequalities the same. That's always our aim. We're always aiming to get those two sides the same. So now what we're going to look at is this piece and this piece. Remember, this is what we know. We know that this is true. So by that logic, we can say, well, if I can prove that 1 plus x times 1 plus kx, if I can prove that that's greater than or equal to 1 plus k plus 1 times x, then we've proved this statement here. So let's do that. So we have multiplied this out, 1 bracket 1 plus kx plus x times 1 plus kx, and that's greater than or equal to 1 plus kx plus x. Multiplying this, I get 1 plus kx plus x plus kx squared greater than or equal to 1 plus kx plus x. Actually, we get a lot of things that will cancel each other out. So the 1's on both sides, kx on both sides, and an x on both sides. So is this true? Yes, it will, because x is a real number. We know any real number squared is positive. K is a natural number. So once k true, once k is greater than or equal to 1, which is what we actually know. So therefore what we've done is we've proved that it's true. So now we've been able to prove it. So therefore pk plus 1 is true. And we have our conclusion. So the proposition is true for n equals 1. If the proposition is true for n equals k, then it'll be true for n equals k plus 1. Therefore, by induction, it is true for all n greater than or equal to 1, where n is an element of the natural numbers.